Okay, so let's talk about linear versus exponential functions. So first, remember linear. It's y equals mx plus b. That's slope-intercept form, where the m is standing for your slope. This is the number that we would add or subtract each time. And then your b is your y-intercept, which is your starting point. So if I look at this equation, y equals 3x plus 2. If I fill out my x's, let's just go with 0, 1, 2, 3, 4. I'd be plugging in 0 in for x. So it would be 3 times 0 plus 2. 3 times 0 is 0, plus 2 more is 2. Then I'd plug in 1. 3 times 1 is 3, plus 2 more is 5. Then plug in 2. 3 times 2 plus 2. So that'd be 6 plus 2 is 8. And plug in 3. 3 times 3 plus 2. 9 plus 2 would be 11. And then 3 times 4 plus 2. So 12 plus 2 is 14. So what did we increase each time? From 2 to 5, we added 3. 5 to 8, we added 3. 8 to 11 plus 3. 11, 14 plus 3. A linear equation will always be adding or subtracting by a number. So let's go ahead and just graph this and see what it looks like. So we need to go to 14. I'll just go up by ones. Perfect. Okay, let's graph our ordered pairs. 0, 2. Left and right, 0, up 2. Okay, we know that's our y-intercept. We could go ahead and use our slope. Up 3, right 1 as well. Is 1, 5 an ordered pair? 1, 5, yes. Up 3, right 1. 2, 8. Yep, 2 8s right there. And then we got 3, 11. 4, 14. So this is a linear equation. I know it's going to keep going up forever. I also know it would keep going down forever. Our domain, left to right, I'll grab my domain and range papers. So the furthest point to the left, when I come in from the left side, I hit it here and it's an arrow. So it's going to keep going left forever, so negative infinity. And then come in from the right side, and I hit that arrow, so it's going to keep pushing, pushing, pushing. So the furthest point to the right is positive infinity. Range, that's our y values. So from the bottom, come up and we hit our figure right there. It's going to keep pushing my paper down. So the furthest, the lowest point is negative infinity, and the highest, coming in from the top, would hit this arrow and it keep going up, so positive infinity. Now let's compare that to this next example, which will be a exponential. So this will be new. It's called exponential because it has an exponent. Okay, so the formula for this is y equals a times b to the x. So a and then b is in parentheses and x is right outside the parentheses. A this time is our y-intercept. So the starting point. And b, don't get confused, they are different. B this time is the common ratio. So this is what we're multiplying by each time. So that would be whatever number we find here. So if I do 0, 1, 2, 3, 4, we see they're kind of similar. They both have a 2 and 3. This time we're plugging in for x, which is the power. So 2 parentheses 3 to the power of x, and we'll plug in 0. So I'm going to grab my calculator for this. I'm going to plug in 2 in the parentheses and then 3 in the parentheses. and then use this little caret key to do my exponent of 0. So that gives me 2. I'm going to plug it all in again. My calculator has a cool shortcut where I could just press second, enter, and then arrow to the left twice to get over the 0 and type over it with a 1. If you don't have a calculator that does this, that's okay. You would just retype it. And I get 6. So I get 2 times 3 to the power of 1. Only the 3 gets the exponent of 1. So let's do to the power of 2 now. 18. So this time I see it's going up much faster. So 2 times 3 to the power of 3. 54. And let's do it again. Wow, this one jumped up quite a bit. Okay, so this time I can see we're not adding the same number. If I went from 2 to 6, that would be adding 4, but it would also be timesing by 3. So from 6 to 18, that's not adding 4 because that would be 10. So adding 4 is not true. It's still multiplying by 3. 18 times 3 is 54, so timesing by 3 is the pattern. We're growing exponentially, very fast that means. So let's write these numbers in, and let's graph this. So on our y-axis, we're going to have to go up quite a bit. So let's try to just go up by tens and see if that works well. Okay, so and let's graph these ordered pairs. The first ordered pair is 0, 2. So do the best I can. 0, 2 would be somewhere pretty low down here. Okay, and then 1, 6, so right to 1 up to 6, so just a little bit halfway there. And then 2, 18, so we're jumping up a little bit more. 3 to 54, okay, now we're jumping up quite a bit. So we jumped up quite a bit. So it's not a straight line, it is a curve. And now 4 to 162, so we would be like even off this graph a couple points, I don't know, maybe about there. So I can see that this might end up going that way a little bit more. And it is curving up. And it's going to keep growing up and up and up forever. So the furthest point to the left would be like a negative infinity. And the furthest point to the right, it's going to keep going up and to the right forever. It's going to slowly get wider, but it will get wider forever, so positive infinity. Now, on this y, so our range from the bottom up, this shape is going to come really close to 0, but it will not actually ever touch 0. So we will say for this one, because it'll keep going lower and lower, but it will not surpass this y-axis. That's how this one is derived. Our range will be, the lowest point will be 0, but it will not be included. So that's the interesting part about this one. And then the highest point is infinity. So what's really important about this is to be able to compare these two. So in a linear example, I have more of an exact straight line. It's going to be adding the same number each time. Whereas in my exponential, it gradually starts. Like if I just had these first 3, I might think this is linear if I just graphed it a little bit off. But if I keep going, I see that it grows very fast. Okay, so we have to be able to compare the two.